And it's steep, and it took me a long time and a lot of effort to get to the top. When I got to the top, my hair started to stand up on end. And now I know what that means. That means there's electricity in the air, and I was terrified about lightning strikes and killing me. I got off that mountain in about 1/100th of the time that it took me to get up. But it's a lovely area indeed. These are called the Pecos Mountains, and it was somewhere around here that Oppenheimer had his own little summer ranch. This is a view from the other side, and these are the Jemez Mountains, and this is the town. This is actually the lab. The town is over here. But this is the laboratory itself, and this part is open. The library is here, but all up in here is very secrety stuff. The Germans who did not understand that carbon could work as a moderator were busy using heavy water. And then the Norwegian commandos destroyed the heavy water plant, of course, in 1943. What they blew up was not the plant itself, but the electrical part. Any of you who have ever seen the old film, The Heroes of Telemark, would remember that. And so they blew up the electrical stuff, and it took the Nazis about 6 months to refurbish the thing, repair it, and then the Americans came over and bombed it from the air, and that was the end. Why they didn't do that either the Americans or the British do that in the beginning and spare the lives of numerous commando Norwegians, I don't understand. But I don't understand why they didn't bomb the railway tracks to Auschwitz either. Anyway, the bombing ended the German efforts at heavy water production and really put the finishing touches on German plans for a bomb. And by February of '43, anyway, the Battle of Stalingrad had been lost by the Nazis, and the tide of the war had really begun to turn. In the Japanese, I keep emphasizing how there are no secrets in science. And the Japanese were also considering atomic energy, first for naval propulsion, and then more secretly even for a bomb. But it was, again, the problems of isotope separation that prevented them from proceeding, and they concentrated instead on the development of radar. Now, by early April of 1943, a decent-sized group of people had been assembled already on the mesa here, or the hill, as it was and still is called. Robert Serber, a brilliant young scientist, was asked to deliver a series of lectures about the newly assembled group with the current status of the bomb project. And basically what he reported on was the work that had been done in the summer group at Berkeley under Robert Oppenheimer that I discussed yesterday. For many of these people, it was the first idea they had of what was going on the Mesa, what they were involved with. There were several senior people, of course, that I've talked about a lot, but the average age of people on the Mesa was 25, so they were mostly young people. I like Robert Serber, who I never got to meet, because in investigating him, it turns out he was born in Philadelphia as I was, and he went to the same high school that I did, which makes me feel much closer to him. And this is what he said. This was his introductory speech. And there is a book now of his lectures. There was no messing around. To produce a bomb, the energy released inside the plutonium or uranium metal creates a temperature close to 10 million degrees. Okay? Now, and of course an increase in the pressure as well. And so the expansion of this material under that pressure and those kinds of temperatures is enormous. And therefore the requirements for an explosion are very severe, and everything has to happen in a millionth of a second. people, I think, are familiar with the term critical mass. And what that means is a mass of uranium-235 or plutonium-239 in which enough atoms fission that you will get the release of these enormous amounts of energy. Now, if the material expands too quickly and the atoms are too far apart, then it's too far for a neutron to go to fission things, and the thing fizzles and becomes sort of an ordinary bomb instead of a nuclear explosion, which, as we said yesterday, is 30 to 40 million times bigger than a normal bomb. And of course, at these kinds of temperatures, these metals are no longer metals, they're gases. And that's a very different state. And this is the reason that slow neutrons can make a reactor, but cannot make a bomb. And that's why nuclear reactors can melt, but can't blow up. Because the neutrons released in the fission are fast. You notice a fast neutron chain reaction. And if you want slow neutrons, they have to make a lot of collisions, each collision losing a little bit of energy. And that takes time. That time is thousandths of a second, which for us is very short. But for nuclear processes, is infinitely long. It's like decades for us compared to seconds. So the time scales in a power reactor of the order of seconds, in a bomb they're order of microseconds or fractions of a millionth of a second. Detonation was also a problem, how to assemble a critical mass. And the first suggestion that was made was of having a male bullet and a female sphere and putting them together. In addition, you need to start the reaction. You need to initialize it, and that takes one neutron at least to start things off. Where was that to come from? What is amusing is that this device, this bomb, is over 70 years old. The technology is much greatly improved. Changed. I don't think improved is a good word. Changed since then. But the initiator method is still classified for reasons that nobody understands. It's probably a radium-beryllium source, which is the original source of neutrons. So you put radium, say, on this piece and beryllium on this piece. When they get together, you get neutrons, and off it goes. Back in 1942, Richard Tolman at Caltech had already talked about an implosion method using explosives. We think of explosions as pushing things apart, but if you surround an object with explosive material, then you push it together. And so you can start with a sphere. Again, this is Serber's drawing. This was a hollow sphere surrounded by various materials which burnt at different rates, and the idea is to squeeze a non-critical mass so small that it becomes a critical mass. And this method is eventually used for the plutonium weapon that destroyed Nagasaki. Plutonium fissions much more quickly than uranium, and so in this case, the bullet has to have a very high velocity. In fact, it was thought that the velocity of this would require the largest gun then in the arsenal of the United States. That turned out not to be quite true. In plutonium, however, it fissioned so fast that even the biggest gun they had would not put the parts together quickly enough. Every country had the talent to do this. Only the United States had the industrial facilities to be able to accomplish it. At the original Serber lectures, these drawings were printed, so both the gun method and the implosion method were being discussed. The only person who was really interested in the implosion method was a man named Seth Neddermeyer. And he suggested, both in these discussions and later in discussions with Oppenheimer, that research into such a technique should be followed. Oppenheimer did not take the implosion method very seriously in the beginning, but he did name Seth the head of the Ordnance Division Implosion Section. And in the canyon below the mesa, this canyon, down here called Frijoles Canyon. Frijoles is beans for those of you who speak Spanish. He set up an implosion area, and they took to blowing up beer cans, and after which, since I knew Seth, he would empty the contents. And they looked at shock waves, and we'll discuss both implosion and Neddermeyer a bit later. The war, of course, was becoming ever more horrible during 42 and 43. January 42 occurred the Wannsee Conference in Germany, and that was the final solution of the Jewish problem was adopted, and death camps began to appear in Poland. In Russia and Ukraine, there were no death camps, but people were instead shot, including all of my mother's family. And the slaughter of millions began in earnest. Over 1 million Soviet soldiers who were captured had starved to death or died of exposure in the camps. In the Pacific, American soldiers on the island of Bataan in Manila Bay in the Philippines were captured, and the Bataan Death March took place, in which most of those soldiers died en route. In Burma, the British were fighting in a war that saw great slaughter certainly on the British side. The troops who died in the Bataan Death March came largely from New Mexico, which meant that when the people in New Mexico learned about what was going on in Los Alamos, there was actually a very positive reaction to it. In Europe, Churchill adopted much of the techniques of the Nazis, of the Nazi Blitz over Britain, to destroy what he called enemy morale. Large losses of bombers caused him to switch to night bombing, which decreased the losses of the British, but also decreased the accuracy of bombing. The British took to bombing civilian areas and civilian housing, again, the idea being of destroying the the German morale, as those of you familiar with Bomber Harris might remember. The days when Roosevelt's claim to try to protect civilians from bombing, those were clearly long past. The bombing of Hamburg in July 43 caused a whole new vocabulary to exist for us, including words like firestorm. The British used incendiary bombs on a warm summer evening, July 1943, and they bombed what was primarily a civilian area, non-industrial and non-military. 45,000 Germans at least were burnt to death. The temperatures were over 1,000 degrees, and the asphalt in the street melted, meaning that people who were trying to flee got stuck and then burnt to death. On every side, the technology of death was really increasing, and nothing seemed horrible enough to stop the slaughter. Oppenheimer, at least, thought that maybe nuclear weapons might be too horrible to allow their use to continue once their power had been demonstrated. That has turned out, I think, to be correct, but it was a concern at the time, because some of you might remember that Alfred Nobel thought that his invention of dynamite and TNT at the end of the 19th century would have the same effect. But all it did in the First World War was to greatly increase the number of people who died. Richard Rhodes, who has done probably more to preserve the history of these events than anybody else, has written the following long thing. And this is a very interesting thing. Nations really have voluntarily limited their claims of sovereignty. For example, the Americans have satellites which photograph everything that happens in Russia and in China, as well as other countries. And so the US has incredible knowledge about, and the Russians don't shoot them down. The Russians, of course, have the same thing as do the Chinese, satellites over the United States, which photograph everything, and they know everything that goes on. Plus, they listen to your and my cell phone conversations, all sorts of things. So this is a loss of sovereignty, as he talks about. Science, going about its business of examining how the world works, discovered a way to spoil war by making it too destructive. And that's probably true. There have been, as I pointed out on Monday, no world wars since. Lots of proxy wars, even proxy wars where a major power loses, such as the Vietnam War. And yet that's acceptable or accepted as opposed to nuclear war. Groves and the Army were considering the problems of producing both the uranium isotope 235 and the plutonium. And as I mentioned, he had bought, months before even Fermi succeeded in building a pile, he had bought the 52,000 acres of land in Tennessee, which is called Oak Ridge. And this led to two methods of separation of isotopes. The first was the gaseous diffusion method, which the British had largely developed. And the second was the use of a cyclotron, in this case called the calutron, for the University of California cyclotron. And I showed yesterday a picture of a cyclotron, and isotopes of different mass rotate at different radii, and I can't resist one more formula. This is the radius of that various materials. B is the magnetic field, which causes them to rotate. E is the electric field, which causes them to go faster and faster. Q is the charge on the particle, and M, its mass. And this is a formula that every undergraduate physics student can easily generate. I remember even doing it myself. But notice it depends on the square root of the mass. So if you take 238, the normal uranium, and you divide it by 235, the desired isotope, and you take the square root of that number, you get 1.0063. 0.6% difference in the radii, tiny and enough. Eventually, 1,152 calutrons were built, infinitely larger than the number of all the civilian cyclotrons ever made. It required an enormous amount of electrical power. But that was a real problem because copper was of such need during the war that there was no copper available. So they used silver. Because this was Tennessee, right next door was Fort Knox, Kentucky, the home of all the gold and silver in reserves in the United States. And so they used silver, which they got 50,000 tons of silver, all of which was returned at the end of the war. It's funny because when the Treasury was approached about getting silver, they said, tons? We talk about silver in troy ounces, 31 grams. 395 million troy ounces of silver were delivered, worth in those days more than $300 million. And as so many men were, there's a calutron, by the way. The particles going around in circles in there. So many men had been drafted that the operators of this were all female. And here's a picture taken of the day. You can see how many, and they're all the women running these things. Directly after Fermi's success in making a pile in December 42, the plant that I mentioned yesterday in Hanford, Washington, to produce plutonium was started. And again, it was put up there because Hanford is in the middle of nowhere in eastern Washington. The Columbia River was right by there, a great source of water, and there were dams on the Columbia River and a great source of electricity. Money was not the object. I already said that this project, the Manhattan Project, cost over $2 billion in the 40s, worth about $40 billion US dollars today. More than 20,000 construction workers were involved. More than 250 buildings were built. Los Alamos used only about 2% of the money. It was all spent at either Hanford or Oak Ridge. Both uranium and plutonium are both radioactive and chemically toxic. So it's a nasty combination. An enormous amount of money was spent on remote handling facilities. Now, people were already familiar with alpha, beta, gamma radiation, so they knew to some extent how to protect against that. But since 1932, the neutron had been discovered, and the neutron could penetrate matter because it had no charge, and nobody knew how to protect against neutrons. They are, in fact, relatively dangerous. They are a terrific creator of cataracts in the eye. Oak Ridge is now still a national laboratory, still does some secret nuclear work, does other work as well. Hanford is no longer used at all, but it is interesting, at least to me, that close by is the site of one of the LIGO observatories. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And last year, the LIGO Observatory, there's another one in Livingston, Louisiana, announced the discovery of wrinkles or waves in space-time, the first time that had ever been discovered due to the collision of two massive black holes somewhere out in the universe, a prediction written down by Einstein in 1915 and never seen before, and that will win the Nobel Prize in December of this year. Work at Los Alamos was, of course, proceeding. The number of neutrons had been carefully measured from uranium-235, which was, as I've said, somewhere between 2.2 and 2.3 per fission. Glenn Seaborg had finally managed to get about 0.2 of a gram of plutonium, which is a speck about 2 millimeters on a side. And that's not much, but it was enough to measure the neutron yield, which is greater than that, and the probability of fission is greater than that of uranium, there being about 2.9 neutrons emitted. There were 0.2 of a gram in those days. There are hundreds of tons of plutonium in the world today. I will show you tomorrow how big the plutonium bomb is. To solve the problems of setting this thing off, of creating a critical mass, whether by shooting an uranium bullet in or having an implosion, they needed somebody on the Hill who was familiar with guns and with detonation. And so they brought in a Navy man who had worked in this field, William Parsons, always called Deke Parsons for reasons I've never understood. and he became head of the Ordnance Division, the blowing up division. Neddermeyer was, of course, working on implosion, and he was using cylinders, beer cans, rather than spheres, because two-dimensional cylinders are easier to calculate than three-dimensional spheres. And he set up in Frijoles Canyon an explosion station, and he could actually compress a can into a solid cylinder. But it was a difficult process because the cylinder was not uniformly compressed. It turned out to be twisted and badly deformed. And this led particularly Parsons, but also lots of physicists, to dismiss his work, with Neddermeyer being called the dreamer. And Parsons is quoted as saying, "Can he blow up a beer can without spilling the beer?" He had a much more practical outlook, but that was useless because the problem of implosion is one of hydrodynamics. It's a problem of the motion of a fluid. And that's something the physicists there, of course, were very familiar with nuclear fission, but I can tell you from having been educated in the field, you don't study hydrodynamics very much, and so they didn't know much. But among these Hungarian Jewish refugees was John von Neumann. And von Neumann was an incredibly brilliant mathematician. He was working at the time at the Institute for Advanced Studies in Princeton, where Einstein was also working. And he knew that the materials driven by high explosives could be compressed to densities greater than 100,000 times that of atmospheric pressure, to densities greater than material at the center of the Earth, which is pretty dense. At such temperatures and pressures, of course, as I mentioned before, solids like iron become fluid gases. And so he proposed using a solid sphere rather than the hollow one I showed you before, and compressing it by surrounding it with implosion, by imploding it with various explosives. And this happens much faster than firing a bullet. And most weapons today are made of plutonium, and all plutonium weapons use the implosion technique. North Korea, which has about 6 bombs, has uranium bombs, and they use the gun method, presumably. Before the international agreement with Iran to limit their nuclear work, they were also enriching uranium. The 2 bombs were labeled Thin Man and Fat Man after Roosevelt and Churchill. And in order to maintain secrecy, because B-29s were being modified to carry these bombs, the word was put out that the modifications were to carry Roosevelt and Churchill to international meetings, the Thin Man, of course, being Roosevelt, the Fat Man, obviously, being Churchill. Eventually, Thin Man, as we will see, was changed to Little Boy, which are horrific names for such dreadful weapons. The British had sent instructions to the Danish underground that eventually reached Niels Bohr, who was then still in Copenhagen. He was sent a set of keys. The keys had tiny microscopic holes drilled in the end and then sealed with metal. He was told to gently file off the end, to syringe out the contents, put it on a slide, dry it out, and enlarge it. And Bohr was a brilliant man and a theoretician. That was completely impossible for him to do. But the Danish army did it for him. And inside was a letter from James Chadwick inviting him to come to to Britain, where he could work on anything he wanted. But his expertise would be very useful on very important problems. Now, Bohr, who was a very smart guy, instantly understood that had to be to do with fission. But he still believed that separating the isotope 235 from 238 was not possible. And so he didn't believe that a weapon could be made. And so he said, I need to stay, he said, to help resist the threat against the freedom of our institutions and to assist in the protection of exiled scientists who have sought refuge here. As I will now tell you, most of the survival of the Danish Jews, and there were 96% of the population saved, was due specifically to Bohr's intervention. At the end of 1943, he was visited by the Swedish ambassador to Denmark, who told him he would be arrested in the next few days. Bohr's mother was Jewish. Even professors are leaving Denmark, he was told, which was a hint. Word from the Danish underground corroborated this, and he left with his wife Margareta that night on a fishing boat that smuggled him over to Sweden. Resistance to the Nazis was increasing in the Danish underground, and it was clear that the tide of the war was turning. Stalingrad was over. Mussolini had been killed by the summer of '43. Italy had surrendered. By the end of August, the Nazis took over the Danish government and, in turn, King Christian X. They planned to arrest all the Jews in the country. The Danes, who had been warned in advance of these plans, had already hidden their Jewish neighbors, so eventually 284 people, mostly elderly people in nursing homes, were arrested and murdered. 7,220 people were spirited away to Sweden, and that exodus was made possible by Niels Bohr. After he and Margareta landed in Sweden, she stayed in the south to wait for their two sons. Niels rushed up to Stockholm. He wanted the Swedish government to protest publicly the arrest of Jews in Denmark as a means of alerting them and bringing some kind of protection to them. He failed at the government level, so he used his prestige to get an interview with King Gustav. Gustav said that, yeah, well, we tried this with the deportation of the Norwegian Jews, and it did not work. But Bohr said, insisted the situation was very different following the loss at Stalingrad and the Italian situation. And the king agreed to contact immediately the Swedish Foreign Ministry. And a radio broadcast was made on October the 2nd, which said the country was prepared to offer asylum. Over the next 2 months, all 7,220 of these people I mentioned came secretly by boat at night from Denmark to Sweden. I knew several of them. There were a lot of German spies in Stockholm, and there were concerns that they would kill Bohr. And so he and his son Oe, his older son, who also won the Nobel Prize in Physics, by the way, were spirited off to England. Bohr flew to England in the bomb bay of a Mosquito fighter lying there, and the plane flew to Britain at a high altitude to avoid anti-aircraft fire as it passed over Norway. And that's at a high enough altitude that oxygen was needed. And so the pilot radioed to Bohr, who was lying there. He had a parachute to be dropped into the ice-cold North Sea if needed. He was not a young man. But his helmet with the earphones didn't fit, so he didn't have it on, and he passed out. Well, when the pilot, who was a smart guy, didn't hear from him, he passed over Norway and then dropped down to a lower altitude. And of course, Bohr was alert and fine when they finally landed in England. He was 58, which in those days was not 58 today, but he was still a very vigorous man. He learned from Chadwick about the progress of nuclear fission. And he also learned that, of course, the center of activity had long since passed from the UK to the US. And so by the winter of '43, Bohr and his son Oe departed for US as part of a British team. The creation of a British team to Los Alamos was both important, interesting, and also ironic. the business, of course, of nuclear fission had really started with the British. And the British, though, had a significant chance to contribute thanks to Edward Teller. Teller began to think that the fission bomb was an obvious problem, okay? A trivial problem. Physicists love the word trivial. I have a friend who considers a trivial problem any one that his brightest graduate student can solve in under a year. He's smarter than I am. Teller was interested in developing the super, a bomb based on the fusion of isotopes of hydrogen into helium and the process by which the sun generates its heat and light. And the energy, as I said yesterday, is anywhere between 7 and 9 times greater. Plus, you can blow up as much of this stuff as you want, whereas in a fission bomb, only a few % of the material actually explodes. This problem of the super was not solved by Teller. It was solved by the Polish immigrant mathematician Stanislaw Ulam, and it wasn't solved until 1951. Nevertheless, Teller was angry and would not work on the fission bomb. He was also really angry with Oppenheimer, who had refused to appoint him head of the theory group and had imposed the German-born physicist from Cornell, Hans Bethe, as head. So he refused to work and left a gaping hole. So Oppenheimer appealed to James Chadwick, who recommended that Rudy Peierls and Otto Frisch come. Peierls being a theoretician, Frisch being an experimentalist. So on board the ship with Bohr and his son were Frisch and Peierls, and also people who made great contributions: William Penny, George Placzek, who made a great contribution, P.B. Moon, James Tuck made a great contribution, Egon Brecher, and last but far from least, Klaus Fuchs. The irony, of course, is that Teller was virulently anti-communist, virulently anti-Soviet, yet the Soviets knew absolutely everything about what was going on because Klaus Fuchs was the most significant Soviet spy. And Fuchs was only there because Teller refused to work on the project. I find that not amusing, but ironic. When Harry Truman, who was president of July in '45, told Stalin at Potsdam about the fact that the US had the bomb, Stalin was not interested because not only did he know, he had detailed drawings from Fuchs about what was going on and the progress that the Americans had been making. Gaseous diffusion at Oak Ridge was a difficult process. Uranium, of course, had to be converted to a gas, which I mentioned yesterday, called uranium hexafluoride, which becomes a gas at about 140 degrees. And it's highly corrosive, making handling very difficult. They had to have a barrier with submicroscopic holes that you could push the gas through so that the U-235 atoms would go a little bit faster. The only material really was nickel, and an alloy of nickel was eventually determined that would work, and tubes of this material were finally constructed. And then you had to have huge pumps to push the gas at a high enough pressure so that you could squeeze it through these submicroscopic holes. And so big pumps were necessary, but big pumps need seals, and you couldn't have grease on the seals because that would contaminate things. And so a special material for seals was developed, which after the war became known as Teflon. Now, there was a big argument between Groves and the chemist leading the Oak Ridge effort, which was Harold Urey, the Nobel laureate who had discovered deuterium. The original nickel barrier had been superseded by a new material, but a plant to produce the original nickel barrier, had already been constructed. So what do you do? Do you build a new plant to create the new material? Do you modify the present plant to create the new material? Or do you use the present material because that's faster? Urey was all for using the present nickel material because he wanted the bomb as quickly as possible. And Groves overrode him and decided to build a new plant and use the new material. And this was a hugely significant thing, and something that few people realized at the time, but Urey certainly did. What it meant that the US was committed to the development of nuclear weapons, not just to defeat the Germans, because they would not be ready really in time to make a significant difference in the length of the war. What it really meant is that the United States was committed to making nuclear weapons a permanent addition to the arsenal of weapons available. Urey saw this and he quit. And he started working only on the control of nuclear weapons and refused to have anything to do with their development. The same problem was faced by Niels Bohr later in a very painful confrontation with Winston Churchill, which we'll talk about. Churchill's hatred of Soviet communism was so great that it blinded him to the fact that nature does not keep secrets the way a nation can. And this political blindness, of course, has caused 70 years of great anxiety. Urey was not the only person concerned about the bomb, because Leo Szilard, who had done everything in his power to warn the US authorities about what was going on in Germany, was responsible eventually for the drawing up of a petition to demonstrate the bomb rather than using it as a military weapon. Science was still a fairly new subject for military and politicians, and they really did not understand that you cannot keep science a secret. And Groves was insistent upon compartmentalization, upon security, etc. What he didn't know, despite all of his efforts at security, was Klaus Fuchs was at the center of the theory group working away. The Japanese knew what was going on. They were considering what to do. The Soviets, under Igor Kurchatov, had already built a secret laboratory in the city then called Gorky, which is now known as Nizhny Novgorod. Groves, with his security obsession, considered Szilard to be a dangerous radical. And particularly since so many of these scientists were Jewish, he was also a considerable anti-Semite. Szilard was convinced, of course, that open discussion and communication were crucial to the success of the project. And openness crucial to science, but for Groves, security was the dominant issue. Already, while Fermi was building the pile in Chicago, Groves wanted to intern Szilard and considered him actually a German spy, which was so ludicrous that was not done, but that was because Arthur Compton protected him. But Groves did put him under surveillance, and it was almost like a comedy film. Reports were written, for example, that said, he met with another man of Jewish appearance. That was Eugene Wigner. They were detected speaking in a foreign language. Well, I mean, these guys were Hungarians, so they spoke in Hungarian. Groves, of course, was terribly suspicious of everybody, particularly of the fact that there were so many foreign scientists. And of course, he missed the real spies. He had David Greenglass in the machine shop. He had Klaus Fuchs at the very center of the theory division. Szilard was allowed to continue working at the Met Lab in Chicago. He was never allowed to work at Los Alamos. But he was concerned as follows. Peace reached by the use of this nuclear weapon before people understood what it would do. If two powers had it, it will lead to, as it did, to a dreadful arms race. By the middle of 43, of course, the Russians were pushing the Nazis out of their country. The US and the UK were engaged in planning for the invasion of France and the opening of the long-desired Second Front in Europe. And these occurrences only heightened the insecurity and fear of the scientists, because they had started in 42 and they knew that they could make a bomb in 45. So 3 years, 4 years. Well, they thought that the Germans had started in 39, and so by 42 or 43, the Nazis would have a bomb. And so there was huge concern. Now, when Bohr came to the United States, he carried with him a drawing of a reactor that he had got from Werner Heisenberg in that fateful meeting between the two men. And the American scientists had looked at it and said, this is completely mad. And so the conclusion could have been, and perhaps should have been, that the Germans were far behind. But that's not the conclusion they drew. The conclusion they drew was that Heisenberg was trying to fool Bohr, and therefore the Germans had made a breakthrough and were way ahead. Bohr had many things on his mind. He was a very bright man. On the way to Los Alamos, he stopped in Washington and he met with Felix Frankfurter, who was a justice on the US Supreme Court. They had known each other for a number of years and were good friends. And Frankfurter had heard of rumors of a secret project going on somewhere. And when he dropped various hints to Bohr was able to say, look, there is a project going on, and it could be one of the greatest boons to mankind or one of the greatest disasters to mankind, and I'm not sure which. Bohr wanted the knowledge of nuclear weapons, of nuclear science, to be under the control of an international body such as the United Nations would soon become. Frankfurter, who was very close to Roosevelt, said he thought that the president would be very open to such an idea. And so Frankfurter met with Roosevelt, and the details of that meeting, which had never been published, are highly controversial still to this day. Was Roosevelt interested in international control or not? Because later that year, he met with Churchill in Quebec, and they wrote up an agreement which made a commitment to perpetuating an Anglo-American monopoly and not making this thing international. And the crucial question, of course, is in limbo, because Roosevelt died before anybody had any idea, really. Truman, who was his vice president starting in 1944 and then became president, didn't even know about the Manhattan Project. He knew that there was something going on, but not what was being done. The problem of the Soviet Union, of course, arose immediately. What to do with the knowledge of the present situation? Should the Soviets be told before the first bombs were built that such a project was underway? This might perhaps, who knows, lead to a conference on the control of nuclear weapons. Or could you let the Soviets discover the ideas themselves? Could the Americans build and drop the bombs and confront the Soviets at the end of the war with a monopoly? The likeliest, this is what of course happened, and the likeliest outcome of that decision and what happened was an arms race and 70-some years of terror for most of us. It would appear that by March of 44, Bohr had a mandate from Roosevelt to begin discussions with Churchill. These were obviously meetings at the highest level. Bohr was a good friend of Sir John Anderson, who was Chancellor of the Exchequer in the government, and as well as a scientist. Most of the British in Washington encouraged him to fly back to London to meet with Churchill and discuss all of this. And Anderson believed that the only alternatives to a major arms race was international cooperation, and so he wrote to Churchill the following: to have this devastating weapon and inviting them to collaborate with us on preparing a scheme for international control. Churchill circled this word collaborate and wrote, "on no account." He was in no mood to see Bohr, and he kept him waiting in London for over a month. And during that time, Bohr received a letter from Peter Kapitsa in Moscow, and to get it, he had to go to the Russian embassy in London, which did not endear him to Churchill either. The letter and the visit alerted Bohr to the fact that the Soviets were well aware of what was going on and the potential of its use in a weapon. Bohr finally got to meet Churchill on the 16th of May in '44, and the meeting was disastrous. Bohr, who arrived with Lord Cherwell, who is Churchill's science advisor, said that he scolded us like two schoolboys. And then 14 years later, Bohr wrote, "We did not speak the same language. It was terrible that no one had worked on the solution of the problems that would arise when it became possible to release nuclear energy. They were completely unprepared. It was perfectly absurd to believe that the Russians cannot do what others can. There was never any secret about nuclear energy." C.P. Snow, who wrote a great deal about this era, said about Churchill in a long quote, which I'll read, "He always had a naive faith in secrets, but he had been told by the best authorities that this secret was not keepable and that the Soviets would soon have the bomb themselves. Perhaps," he goes on, "with one of his surges of romantic optimism, he deluded himself into not believing that. He was only too conscious that British power and his own was now just a vestige. So long as the Americans and the British had the bomb in their sole possession, he could feel that power hadn't already slipped away. It is a sad story." That's the end of the quote. When you think of the money that has been spent in the last 70 years and continues to be spent, trillions of dollars, plus an enormous number of unreported accidents that you probably do not know about, but that I have some knowledge of, near misses, close calls. It's a really tragic situation. Bohr stayed in Britain until just after the Normandy invasion in the 6th of June, and then he returned the week after to the US. He spoke again with Frankfurter in Washington and reported the dismal experience. Frankfurter went directly to Roosevelt, who was amused by Churchill's pugnacity in what had happened. But as Frankfurter went on to write, "We are in a completely new situation that cannot be resolved by war. It was a far deeper interference with the natural cause of events than anything before attempted, and would completely change all future conditions of warfare. No one would be able to win. A spasm of mutual destruction would be possible, but not war." And ultimate power had really appeared, and Churchill failed to recognize or understand with it. Major nuclear war between the superpowers would not have any winners, it would only have losers. And this has, of course, become even more true with the development of the hydrogen or fusion bomb. Here's Bohr writing in 1950, "Offer unique opportunities to bridge international divergences." Now, Bohr was not a fool, and he understood the suspicions of nations and their leaders, the inequalities, social problems in states throughout the world. But he saw how how useful and effective openness was in science. He also lived in Scandinavia. The three Scandinavian countries had been amongst the most warlike in Europe for centuries, from the days of the Vikings on. And they had invaded one another. They had invaded Europe. They fought. They were the major power on the Protestant side in the 30 Years' War. Yet they now lived in cooperation and reasonable peace. And Bohr was hopeful that a similar situation might be able to develop between the United States and the Soviet Union. Bohr discussed these problems with Roosevelt, and he felt that he was positively received. But then Churchill and Roosevelt met in September of '44, and Churchill just overwhelmed Roosevelt with his dislike and distaste. Who is this Bohr, and what is this all about? Bohr should be confined, or at any rate made to see that he is on the very near the edge of moral crimes. Churchill never understood that nuclear fission and later thermonuclear fusion are not acts of parliament. They are deeply embedded in the physical world. They were discovered because it's possible to discover them, and they are beyond the control of human beings to hoard. Despite the great pressure, there were other people interested in this problem, in particular Vannevar Bush and James Conant, who were running the project, and they wrote this long thing about trying to set up some sort of association of nations, and there will be great resistance to this measure. But the hazards to the future of the war are sufficiently great to warrant this attempt. This is still true, and made perhaps even truer now that we face climate change as an equally grave threat. To get back to the weapons, early in '45, the gun method seemed as sure a thing as any untested technology could be, and awaited only enough separated uranium. At Los Alamos, Emilio Segre had calculated the critical mass and purity of U-235, and it was decided that the muzzle velocity of the gun to assemble the pieces could be reduced, and so that you needed only a gun about 2 meters long and a total mass of about 5,000 kilograms. These are easy things to put inside a B-29. So the Thin Man design was shortened and renamed Little Boy. Plutonium, of course, reaches a critical mass much more quickly, and the implosion took on increased importance. The two-dimensional work of Neddermeyer was not going very well, and Oppenheimer decided he needed help. He appealed to James Conant, who was, as I said, president of Harvard. Conant sent him a great Harvard chemist, George Kistiakowsky. And George Kistiakowsky arrived in January '44, and he worked into a hellish situation. Deke Parsons, the head of the group, wanted everything run militarily, conservatively. Seth Neddermeyer could not have been a more different human being. They never agreed about anything. And neither of them wanted Kistiakowsky there. So the Parsons-Neddermeyer-Kistiakowsky arrangement was a most unhappy one. The other personality clash, of course, was between Teller and Hans Bethe, or between Teller and virtually everybody. The conflict between Neddermeyer and Parsons and that between Teller and Bethe are examples of what could happen when great pressure is exerted on people whose psyches are every bit as fragile, if not more so, than most people's. Oppenheimer and Kistiakowsky worked out an arrangement whereby Neddermeyer was basically removed from the project by being made a technical advisor. Kistiakowsky would now work directly under Parsons, taking charge of all the science. Neddermeyer had no choice but to agree, and was very bitter. And I knew Seth in 1970. We used to drink a lot of beer together, he and I. And he still would go on, depending on how much beer he had, about his dislike of Oppenheimer. As plutonium started to arrive, there became a serious problem. Plutonium-239, just like, was not the only isotope in the material. There was also a lot of plutonium-240. Now, U-235